What I'll be doing for this last chapter is putting the PowerPoint slides after the textbook lecture. This will be sort of like a little review to get us going. And in, again, section 1, we're talking about composite and inverse functions. And there are the topics we've mentioned. So a little summary: in the real world, functions frequently occur in which some quantity depends on a variable that in turn depends on another variable. So this relationship is called composite functions. And here we see an example of composite functions where the function of g is this, the function of f is this, and let's go through it. So here we're saying that if we have a 1 and we put it into our machine, which is the function, 3 times 1 is 3 plus 1 gives you the 4. Now with this new value, we put that into the next machine, which is 1/2 of 4, which is 2. 2 minus 3 gives you the 1. So again, this input gives this output. This output now becomes the input, which gives you the output. Since f takes the output from g, we can combine f and g to get a new function, h. Now, this is written in a certain way, and part of what you need to work on, and I know I had to repeat this a number of times to get a good handle on it, is that here we're saying the function of g now would then be whatever this x was. This machine is this. This is what x is. So we put 1/2 then of this, that again came from the other, to give you this new function. So when you calculate this, it's 1/2 of this, 1/2 of that, and then we have to integrate this 3, which is actually a -6/2, then you get this. So this is the new machine then, which is a summary of the other two. This function h is the composition of both these other functions f and g, and is denoted by a couple of ways to read this. The composition of f and g, the composition of f and g, f composed with g, or f circle g. And again, you may have to write that down somewhere, repeat it a number of times to get it from short-term memory into long-term memory. So, in summary of how to write the composition of functions, where you have this, you could define it this way. So there's the symbolism, and then there's the, in a sense, not a shortcut, but these are equivalent. And again, through repetition, hopefully you'll master it. Now, we say a picture is worth 1,000 words. So here's a little picture of what this composite of these two functions would be. So your x is your original input, whatever it happens to be. It goes into the machine, the function g. That comes out, and by the way, this is a new x value here, which goes into the function of f, which now comes out as your final function, your results. And that's what they're trying to show you, and you'll be working on this in your homework. So let's take a look at this particular example. Now here they're giving you the function of f, which is, I'll get my pen going here, which is this, and the function of g, which is this. So they want you to find f composite with g, or f circle g, and also they want you to reverse this to see what happens. So when you do these, again, the first thing you do is you take your g function, which is right here, and then we put that into our f function. So let's take a look at it. So that is our g function right there. And we have to add the 4 to it right there. So we go 4 times x squared is this, and 4 times 2 is that. Okay? I would have put that 4 there probably earlier than they're showing it, but again, they're putting this where the x is. And the 4 goes along. Again, I would have put the 4 there, but hopefully the book knows better than I do. So now, that was where f circle g. How about now g circle f? Well, now we're going to take the first component, which is this, which is our first item, and now we're going to integrate this as our x into this x. So let's watch it. So remember, our x here is x squared plus 2. So where the x is up here, we substitute 4x. So there's our 4x. We square this and add our 2 together. So these are our results. Now, keep in mind, this example shows that in general, when you have f circle g and g circle f, the results are not equal. This does not equal that. And they're showing us this example. Okay, and you'll have some practice on that. And in fact, I want to go to some review, so I'll pause this here. Now, we're taking a little detour. We're going into the practice examples in your study plan, dealing with composite functions and inverse functions. And they're asking us to use a table to evaluate the expression. Now, when you see something like this, G circle F, 2, well, what we do is we go to our F function first, and we look for a 2, which is right there. Now, when this is 2, the result is a 6. We then go to our G, where there's a 6, and that gives us a 7. And that's what we put. And then that is correct. Now here, it's saying F circle G. So we look for G first, where the value is 5. So there's G. The value is 5 right there. We then go, the results is 6. We then go to our F, where 6 is, and then we get a 2. And that's what we put in, and that is correct. Now, here we're saying G of G is 6. And in the sense there is no value for that. So something like this is undefined. And we check our answer, and we see we got it right. Okay, I just thought I'd introduce that a little bit because in our textbook and in the PowerPoint slides, they're not giving this. Keep in mind, anytime you get a problem in practice, then you would just jump over to help me solve this, view an example, and again, our textbook doesn't help that much here. Okay, we'll go back to our PowerPoint slides. So we're now getting some background on inverses and one-to-one functions. Let's view the following two functions as relations or correspondences. Now remember, these two words are sort of like synonyms. That is, they mean the same thing. So here we have states, which is the domain. So these would be our x values, our inputs, and in our range, we have outputs, and we're saying main is 1, and this has to do probably with representatives maybe in Congress, but they're not telling us that. Illinois, there's 7. Iowa, there's 2. Ohio is 3. So one line from the x going to the range, which are the y's, and it's a one-to-one relationship. Now, when we go to toys, we get a ball and rope, gym, phone, gym, car, jack. Now notice here from the domains, there's an x and a range y. Now our domains, notice, is not a one-to-one relationship. It is a function because the domain item is used only once. But because Jim has two things, it's not a one-to-one relationship. So sort of keep that in mind. Now, in an inverse relationship, the general thing we do is we had our original relationship as an xy. In an inverse relation, we reverse it. The y items now become the domain, and the x items now become the range. That's what the inverse relation refers to. So our domain, which is on this side now, which used to be our y's, these are our new x's, and these are our new ranges. Now in the states, can you see it's still a one-to-one relation and is a function. But when we look at toys, we see our domain now, our x values. Since Jim is used twice here, this no longer is a function in its inverse relation. And that's what they're explaining here. In the state functions, different inputs have different outputs. So it is a one-to-one function. In the toys function, rope and phones are both paired with Jim. Thus, the toy function is not one-to-one. All right, it's just reviewing what we said. A function is one-to-one if different inputs have different outputs. That is, for A and B in the domain of F, with A does not equal B, we have the functions do not equal. When the function F is one-to-one, if a function is one-to-one, then the inverse correspondence is also a function. Again, just putting to words what we had said already. The graph of every function must pass the vertical line test. And let's do a little review of that. Okay, I did some preparation on this slide. The vertical line test, you recall, is we take this very thin vertical line and pass it over the face of our graph. Does this vertical line intersect this graph in more than one place? And the answer is no. So it passes, we say, the vertical line test, and this is a function. Now, does this same vertical line, as it passes over this parabola, didn't make it too well, but does it pass the vertical line test? Yes, the vertical line says that, yes, this is a function. Now, we also have what is called the horizontal line test. And I didn't put the horizontal line over here. Let's do one. Now, as this comes down, does this horizontal line intersect this graph at only one place? And the answer is yes, it does. So it passes the horizontal line test. So its inverse is also a function and is a one-to-one relation. But how about this parabola? As this horizontal line comes down, it's going to intersect there and there and there and there. It does not pass the horizontal line test. So its inverse is not a one-to-one relation. So let's check that out. If it is impossible to draw a horizontal line that intersects a graph's function more than once, then the function is 1-to-1. That is, if it only does it once, it passes the 1-to-1 relationship. It's a function. But if it intersects it twice, like we were just showing, it is not. So determine whether this function, which is a parabola, is 1-to-1, and thus has an inverse that is a function. Well, there's this parabola, and we see the horizontal line, which is illustrated as a dotted line that's passing down, intersects more than once. So this is not a 1-to-1 relationship, and its inverse is not a function. Now, when we are finding formulas for inverses, again, you need to pay special attention to this. Now, when the inverse of f is also a function, that is, the original would pass the vertical line test, only intersecting in one place, then it has an inverse, and it is read f inverse. This is a function symbol. Now you may recall that we sometimes had negative exponents. This is not an exponent. This is the inverse function symbol, and it's read f inverse. And they give you this right there a couple of times. So, how to find the formula? First, you make sure that your initial function is 1-to-1. Then you replace the original function, switch the x and y's. Well, the first thing you do, let me give you an example here. So this would be f of x equals 2x plus 1. And this is a linear equation. It is a 1-to-1 relationship, so it does have an inverse. Now, the first thing you do is replace the function symbol, that's what they're saying, with a y. Now, the next thing you do is you interchange the x and y. So this is y. We're going to put this x there. We're going to put the y there. And we've done exactly what they've said. Now we solve for the letter y. Well, we're going to transpose this 1 to this side, becomes a negative 1. And now we divide both sides by 2. And our new equation now, where this is y, we then put f inverse equals x minus 1 over 2. So we replace y, this y, with the f inverse. This is the inverse function notation. All right, we worked out a nice little example here for you. Now, one of the things I have found, though, that's useful, because they'll ask you to graph this, is if I take this, when it was in this form, y equals x minus 1 over 2, and I want to graph that, I'm going to go y equals, put this 1/2 x, this is 1/2 x over 2, minus 1/2. So I now have it in slope-intercept form, where there's my new y-intercept and there's my new slope, compared to the y-intercept there and the slope there. Little technique that I thought might be useful. Okay, let's do this one. Now it is written out, but I like doing it a little bit. We're going to replace this with a y. We're going to reverse the x and y. Put the x there. Put the y there. Solve for y now. Transpose that 2. Divide everything by 5. Now they just put it all over 5. I like it this way if we're going to graph it. So this now becomes y equals 1/2 x. How about 1/5 x? That will be better and correct. Minus 2/5. Now remember, they want you to write it this way. F inverse equals x minus 2 over 5. So when you put it in MATLAB, write it this way. But if you're going to graph it, write it this way. So there we start. Replace the y for the symbol there. Reverse our letters and solve for y. And then put your inverse symbol. Again, I had left out the x. You should put the x there. Normally, when you do MATLAB, they'll have this written out for you. You just have to write this part. All right, they're also going to ask you to graph some of these. Most of the times the graphs are given and you have to pick them out. So you won't be physically doing them. Here they put the line in ahead of time. So we have the graph of this, and we now want to graph its inverse. So what they've done is they've put this here, and remember, when you're graphing this, this is y. So our y-intercept is -2, right there. Our slope is 5 over 1. So you go over 1, and then 1, 2, 3, 4, 5. And that will give you your primary line. Now when you go to graph this, which is x over 5 plus 2 over 5, that's the inverse. Remember, your slope now is going to be 1/5, and your y-intercept is 2/5. So let's see if I can plot that here. 2/5 is about there, and the slope is 1 over 5. So I'm going to go out 5 here, and I'm going to go up 1. So there's my other line. Now, one of the things we also note is that when we do the inverse of them, we actually are getting a reflection of this red line. And keeping in mind that the axis of symmetry, or the line of symmetry, is y equals x, which if I graph that now in, let's say, green, is right there. Let me get it right here. There we go. And they usually make this with kind of a dotted line. And if I had a piece of paper, if this were on a piece of paper and I fold it along this green dotted line, can you see this line and this line would overlap, as would this and this? So if I made this red line with, let's say, some free ink that would be copyable, when I fold the page over, it would make this line. So that's why we say this line is the reflection of this line. This is your major function. This is your inverse function. And we worked it out here for you. All right, there's your axis of symmetry. And there is the other line. Okay, well done. We say the inverse of f is a reflection of the graph across the axis of symmetry, y equals 1x. Now, let's consider inverse of function in terms of a function machine. Again, good little visual here. So here our x's are coming in, and they're producing our outputs. So we have a value here, we have a value here. Now if we reverse this, and we could look at either of these, and this one or that one first, we're putting in our inputs this way, these inputs, and going through the machine, we end up with our outputs. So here, the outputs are the inputs, and vice versa. A nice little system showing what's going on. So, if we were to actually solve this, and I do this in the textbook version, when we do it, here the output should be x, and here the output should be x. That is the same. So let's show that this, being this, and this, which is its inverse, equals x. So we're taking our x and putting this where the x is. We're then cubing it, and that is the one that's up there. So when we cube the cube root of something, it just becomes the radicand. So x minus 1 plus 1 is x, so that one checks out. And then when we do the other, that is, put it all under the radical sign here, there's our x, which is actually this, and we actually don't see the bottom here. There we go. We get x as well. So it does check out. And that will wind up this lesson. Now I want to do some examples from our additional exercises that will help support what we've done. Here we were doing theory and a few examples.